I would like to thank Dmitry for inviting me here to give the seminar. I will speak about some geometry of integrable discrete systems. I will speak first on the geometric meaning of the discrete KP equation in the version of Hirota, and then in its non-commutative version of Nimmo. And I will show that from geometric point of view, non-commutativity is something very natural. And then I will present a kind of reduction from the generic non-commutativity to quantum, in the sense that some variables which are involved in the equation will satisfy some commutation relation, which are quite standard Weyl commutation relations. But I would like to present to you this as a kind of surprise, which I still probably fully do not understand, because the Weyl commutation relations appear very naturally from the requirement of ultra-locality. Okay. So first two slides will be a kind of motivation of my work. So about 40 years ago, Ryogo Hirota, when he tried to summarize his works on the bilinear equation, integrable equations which you can solve using his bilinear method, he found the very generic equation initially in 3 discrete variables. So I, j, k, so first, second, and the third variable. And here the subscript in brackets means the shift in the corresponding discrete variable. So this equation appeared maybe in quite a bit different form in works of Hirota. And its connection with the Kadomtsev-Petfiashvili equation and its hierarchy was clarified by Miwa 1 year later. So sometimes this equation is called also Hirota-Miwa equation. So I would like to recall that the Kadomtsev-Petfiashvili equation is just this equation in 3 continuous variables, x, y, and t. But this equation allows for infinite sequence of commuting symmetries, which are called higher time variables of the Kadomtsev-Petfiashvili hierarchy. In particular, first 3 variables from this infinite sequence are x, y, and t. And Miwa found that if you define a collective shift, so each time in the hierarchy, in the solution of the Kadomtsev-Petfiashvili hierarchy is shifted by lambda power k divided by k. So this is a kind of collective shift in all time variables. Then you can interpret one shift related with a particular lambda parameter. So you can have parameters lambda I, lambda j, and lambda k. And if you interpret these collective shifts as steps in the discrete variables, then you obtain that some function tau related to the solution V of the Kadomtsev-Petfiashvili equation satisfies the Hirota equation. So you have a kind of discrete variables. You have some coefficients in front of the tau. Here, you do not have any coefficient, but this is nothing very important. So to summarize this first slide, we have an integrable equation which can be solved by various methods from integrability theory. This is discrete equation. Related to the Kadomtsev-Petfiashvili equation and to the whole hierarchy of equations via this Miwa transformation. But important thing in the discrete KP equation by Hirota is the following observation, that if you formally add the fourth discrete variable to the equation, so suppose you have equation in I equal 1, j equal 2, and k equal 4, yes, then this new equation is compatible with the previous equation by Hirota, in the sense that it provides a symmetry of the Hirota discrete KP equation. So the equation, the form of the equation is its own symmetry. Yes, so the fourth variable, the fifth, the sixth, and so on, can be considered as symmetries of the equation. Moreover, they commute between each other. So this is a very simple observation, and in fact it could be discovered 40 years ago. Okay, but this point is something very important from the point of view of integrability. So in a sense, to recapitulate, the Hirota equation can be formulated in infinitely many discrete variables, and the higher discrete variables are symmetries of the original equation, which can be formulated in the first three variables.
Adam, could you say some words about the continuous Hirota equation in this context? So is it also the symmetry of, is the discrete one is the symmetry of the continuous one for the Kadomtsev-Petfiashvili equation, or are they not connected?
So you can interpret this indices in brackets, not as shifts, but as derivatives. Yes, you can formally write down such an equation where you have derivatives instead of shifts. And such equation appeared first in works of geometry. There is a kind of differential geometry of webs, but it also appeared in the papers of Gelfand and Zacharewicz. And it was a kind of most general equation integrable by the method developed by Ilya Zacharewicz. So that's why it is sometimes called dispersionless Hirota equation. And it turns out that this dispersionless Hirota equation is also multidimensionally consistent, in the sense that you can write it down formally in infinitely many continuous variables, and the variables, the fourth, fifth, and sixth, and so on, continuous variables provide symmetries of the original dispersionless Hirota equation. So I know that this fact about multidimensional consistency of the dispersionless Hirota equation appeared in works by Wojciech Kryński, but I do not know its relation to the Kadomtsev-Petviashvili equation. So maybe someone from the audience knows more, but certainly the dispersionless Kadomtsev-Petviashvili equation is not the dispersionless Hirota equation.
Adam, you say the symmetry commute. Usually in continuous case, when we have, algebra of symmetries, they commute like we have Lie bracket. In what sense your symmetries commute? Because we have a discrete equation in this case, and symmetry is discrete, right?
In a sense, like the Backlund transformation. You can interpret the fourth variable of the discrete Hirota equation as a Backlund transformation, and you can formally treat this equation, which involves, for example, the first, second, and the Backlund transformation variable, as a Backlund transformation of solutions. So you first have to show that if you have a solution of the Backlund transformation equation, it provides you a new solution of the original equation. Moreover, you can check the Bianchi permutability diagram. So in a sense that if you have two symmetries with some initial data, then these two symmetries mutually commute. So if you have 1 + 1 dimensional equation, then instead, then your initial data are just numbers, parameters. In multidimensional equations like the discrete Hirota equation, you have to also transform correspondingly your initial data. So, but basically, you can interpret the additional variables as the discrete Backlund-Darboux transformations. And commutativity is just the Bianchi commutativity diagram of the Darboux transformation.
Adam, thank you.
Okay, and now this multidimensional consistency, I think, was overlooked, and it was, I think, put in the proper context by Niyov and Adler-Bobienko-Suris. And this is an example of 1 + 1 dimensional equation. So this is the discrete modified Korteweg-de Vries equation. This involves some parameters, lambda I, lambda j. So this is the form of the equation. And variables live on a quadrilateral. So you have variable v, shift in I, shift in j direction. So from 3 v, vi, and vj, you calculate vij. Yes, but it turns out that there are 3 ways to calculate vijk from the data v, vi, vj, and vk. And it is, I mean, interesting observation, because you can calculate it. You can check by calculation that the 3 different ways to calculate vijk give the same result. But you can also interpret this observation as something very important. For example, to select integrable equation from some quite generic equations. Yes. And also here you can interpret the 3rd variable as a Darboux-Backlund transformation variable of the equation living on n1 and n2 variables. And to connect to Yang-Baxter equation, it is interesting to reformulate the discrete modified Korteweg-de Vries equation in terms of fields ui. So ui is vi divided by v. And these fields ui live on edges of the lattice. So you can have the transformed form of the equation. Okay, and this picture below shows you how you should interpret the multi-dimensional consistency of the equation in this edge form of the equation. So if you calculate the field along blue arrows, the result should be the same as you calculate the field on green arrows. Yes, and also I would like to stress that the edges of the quadrilaters are oriented. Yes, so you have ui and uj fields on oriented edges, and this is the transformation from ui and uj to their shifted values. But now you can somehow modify a bit the form of the equation. So instead of having ui and uj, you perform a kind of partial inverse of the map. So suppose you start from x and y, and you calculate x tilde and y tilde. Yes. And you define, if you can perform such partial inverse, you define your map as R, and now this is map of two variables into two other variables, but you can somehow enlarge your space of variables. Instead of two, you can consider three variables, but now map R acts on corresponding pair of variables. So for example, R12 acts on x and y. R13 acts on x and z. And R23 acts on y and z. Yes. And in this form, the multidimensional compatibility or consistency of the equation can be formulated as a kind of functional Yang-Baxter equation. So this partial inverse is called the companion map to the discrete modified KdV map. And from this point of view, the multidimensional consistency is equivalent to the Yang-Baxter condition. And just to recall, that original quantum Yang-Baxter equation was formulated in terms of operators acting on tensor product of vector spaces. Yes. Okay. Okay, so this was a kind of generic motivation for reconsideration of discrete Hirota equation, discrete KP equation, but also with some geometric sense of the equation. So now I will consider the so-called Desargues maps and their relation with the Hirota equation. So the initial definition is something very simple. We consider maps from n-dimensional integer lattice, Zn, into projective space. Just for those who do not like projective geometry, you can just consider maps into the standard affine space. Yes. In particular, in the affine space, you know what a straight line is. Yes. So you know that through any points of the space, there pass only one. If the points are different, of course, there pass only one straight line. So you impose a requirement on your map. You need only that for each discrete variable n, the point phi of n and its two neighbors in I and j direction are collinear. Yes. And in general, if you have any field, you can consider m-dimensional affine space over over the corresponding field. So you can consider the field of real numbers, the complex numbers, also finite fields, also some other interesting fields which do not have to be commutative. So, for example, quaternionic field, which is called in this context by various people division ring. So you have ring, but you can invert any non-zero element, and the ring is associative, but it doesn't have to be commutative. So you can formulate projective or affine geometry over such division rings, and you only should take care that you multiply your vectors from one side only. Yes, so I will consider such a rule that I am allowed to multiply vectors by elements of the field from the right. Yes, and this is also something natural, that we can represent affine space by coordinates. Yes, so, but some vectors. In projective space, you just consider vectors of one dimension more, but two vectors represent the same point of the projective space if they are proportional. Yes. So it is somehow convenient to use this freedom to represent element, a point of the projective space as a array of vectors. So any vector multiplied by an element of the field by a scalar gives you the same point of the projective space. Yes. And this simple collinearity assumption gives you an equation. So geometrically, it is that the point phi 1, 3 should belong to the line passing through phi 1 and phi 1, 2, and it should also belong to the line passing through phi 3 and phi 2, 3. Yes, so by intersection of two lines, we obtain new points of the map. And in terms of coordinates, the collinearity of points is reflected by a linear relation. Yes, just linear equation, and the compatibility of linear equations gives you a nonlinear equation. Yes. So these coefficients ijk, which are functions of discrete variables, are not free. If you have any Desargues map, I mean, defined by this collinearity, you have also a solution of this nonlinear system. Yes. Of course, the gauge freedom means that some fields in this nonlinear system are redundant. So let me fix the gauge in a sense that I will impose an additional requirement which doesn't spoil this collinearity, and it is also, and geometrically does not involve additional restrictions. So very natural from this point of view is the so-called Hirota gauge, where this linear equation is reformulated using only one field, Uij. One can check that, one can show that it is always possible to introduce such a gauge. Yes. And in this form, the nonlinear system splits into the following part. So first part Uij plus Uji equals 0 is just follows from the form of the equation. And the second also follows from the form of the equation, but somehow it reflects that you can formulate this equation from the linear system. You can consider linear system in 3 discrete variables, and also there is this constraint, which is the direct consequence of this constraint for A. Yes, and it turns out that this set of equations was formulated by John Nimmo, and he called it the non-Abelian Hirotamiwa equation. And indeed, when the field is, or the division ring is commutative, then the last equation allows you to introduce a potential tau, and the second equation can be rewritten then as the original Hirota discrete system. And we know that the system is multidimensionally consistent. Yes, one can check that. And now there are 2 questions. The first question can be asked by a person interested in dynamical systems. So what is the counterpart of this multidimensional consistency on a level of a higher dimensional analog of the Yang-Baxter equation? Yes. And another question can be asked by a geometry-oriented person who can ask, okay, there was geometric definition of the equation. We know by calculations that this equation is multidimensionally consistent. What is the geometric counterpart of this multidimensional consistency of the equation, of the discrete equation? Okay, so first, I will ask the first question. So we can interpret the discrete Hirota equation, so this system, as a map from fields living on faces of a cube. Yes. So in vertices we have wave functions phi. On faces we have fields. Yes. And the Hirota equation is a transformation from these three fields to these three fields, shifted. Yes, like we had in the case of discrete KdV equation, fields living on edges. Now we have fields living on faces. Yes, so in this formulation, phi is in the center. Yes, but let us have the same cube, the same fields, but let us again try to make a partial inverse of the map. So y1 and y3 are the same like before, yes, but y2 is the field which lived on the new faces. So in this formulation, where phi is in the top vertex of the graph of the cube, yes, we have a map from y1, y2, and y3 into new variables, and just elementary calculations show you that you have such a map. Yes. So it is the companion map to the non-Abelian Hirota map. Yes. And now, instead of, because now we have equation living on a cube, so we should consider four-dimensional consistency. And now this is what we have in this case. We have four-dimensional cube, and instead of the Yang-Baxter condition, we have Zamolodchikov condition, and here is the corresponding picture. So we have initial fields living on six faces of the four-dimensional cube, and each map has corresponding variables which are touched by the map. So R1 to 3 involves this 1, 2, 3 faces of the smaller three-dimensional cube, and so on. So in this way, we go over all faces of the four-dimensional cube, and we can obtain the same result when doing the operation on in the right direction or in the left direction. Yes. So this is just combinatorics. If we know that the maps are well defined, yes, then if the equation is multidimensionally consistent, then the following functional condition should be satisfied. And in the non-commutative case, it was shown for the discrete Hirota equation in works of Kashaev, Korepanov, and Sergeev. Okay. So the map is very simple. Yes, a simple transformation. And basically, you can try to check.
Excuse me, so just a small question.
Yes.
So if you will consider not symmetry, your ij plus uji equals 0, but you consider skew symmetry, then you can apply transformation uij equal tau I divided on tau j.
Aha, so I didn't consider that. So you mean that instead of having...
Yeah, so this is Uij, so you define it's in this form, and then it's so it is you have a kind of symmetry. But if you define it just ti in bracket divided on tj in bracket, then it would be then you can do the same machinery, but then you will get else a solution, another solution to this equation. Else you can continue what you do on your next slides, and then it would be else a solution to the Zamolodchikov, but it would be related to some kind of multiplicative. So it would be so in your case you have so you have in your case you have so all this y1 tilde y2 tilde plus y3 tilde is equal y1 plus y2 plus y3. So you have kind of this first integral. But if you do this transformation, then you will have product. Then it would be, say, y bar, y2 bar, y3 bar is equal product.
Yes, I understand.
Okay, so and therefore question, so what, so it's just, this is symmetry, it comes from Drinfeld. So your condition ui plus uji equals 0. Because this would be different in these two conditions.
Yes, yes, I understand. Okay, okay, thank you. So it is an old result, or?
So this is a relation, I think. So what your transformation is called Lustig. So if it is in the sense in the language of braid moves. So if you have just reduced decomposition, and if you have so-called Lustig data, then this will be correspond to Lustig transformation if you just make braid move. And what is with multiplicative, it is so-called string data, and then it's called Bernstein-Zelinsky transformation.
Okay, so thank you, interesting. Okay, so if you have such a map, you can try to calculate this equation. Yes, to check this equation, and you can try to do it on by a pen and a piece of paper. So I tried to verify this using MATLAB, and there are I think six identities which should be verified. But my MATLAB worked for some identities. It worked few seconds, even milliseconds, and and there was one identity where MATLAB was not able to check if it's true or not. Maybe it needed a guide, but it turns out that this is a better way to check this identity. And there is nice device. I think I found it in papers of Sergeev and Korepanov, that the map for Y, yes, can be written using matrices. So define a matrix 2 by 2 in such a way, yes, and you can have its very natural 3-dimensional extensions. Yes, so it turns out that the same map as before can be rewritten using these 3 matrices, and this has a form of the Yang-Baxter equation. Yes, but now you have some parameters y1, y2, and y3, and tilde parameters in this way. So if you if you check what is on the level of y variables from this metric equation, then you have this simple 3x3 equation, which is equivalent to this yellow, to this blue transformation formulas. Yes. And
I ask something. So it's true, yeah, I mean, Sergeev, Kashaev, and Korepanov, yeah, do state that if this local Yang-Baxter equation uniquely defines a map, if you see it as a matrix refactorization problem, so if it uniquely defines a map, this is a solution of the tetrahedron equation.
yes.
The question is, you started already from the map. Is there any systematic way that you can write a map in its this matrix refactorization relation?
So this local Yang-Baxter equation can be interpreted if you know geometry of the equation. So in general, I cannot I do not know the answer how one can perform rewrite the map in terms of local Yang-Baxter equation, but sometimes geometry gives a hint. And in this case, the geometry of the map, I mean these straight lines, allow you to formulate this map in terms of local Yang-Baxter equation.
So I was wondering, so there is in Frank's Neyhoff work, there is the following statement. So if a discrete system, integrable system of difference equation is strictly consistent or multidimensionally consistent, then you can algorithmically construct this lax representation with no geometry, just simple linear algebra. And since there is you know, this 3D consistency is kind of equivalent to this local Yang-Baxter equation, I was wondering if there is somehow a similar way to work in his method, in Frank's method, to write for a map, to write if it's a representation, not necessarily geometrically. So can you comment on that?
So, I mean, I know, for example, for this map, there is another matrix refactorization formulation, which written in terms of, I don't know, using some Heisenberg algebra matrices, but I don't know how it is useful for this Zamolodchikov equation. So I cannot comment about the general. But at least I know that for this map it is another refactorization problem related to this map, but I think it was not used to find solution of the Zamolodchikov equation. Okay.
I can add that the local Yang-Baxter equation sometimes is not unique for the solution of the tetrahedron equation.
Yeah, but sometimes it gives you correspondence, and you can add consistently some, choose some values of this correspondence so that it defines a Yang-Baxter tetrahedral map. So,
okay. So now I would like to answer the second question, geometric equation.
Adam,
yes.
Adam, you know, I have, you know, one proposition to the seminar in general. I already write to Dmitry. You know, your talk is very interesting, but I'm afraid that if you will try to explain everything today, it will be very jam. You know, it's because you proceed only maybe less than half of the talk. Maybe we you do in this nice pace and explain everything as you do, and if not fit this seminar, we can continue next time. We can arrange if it, you know, okay with you. I think
you see, for me it's okay.
me is okay. What about others?
It's better to be slow and understandable than you know, finish your slides and
yeah, because I think, you know, if you will try to fit, you will accelerate and we lose details, and that will be not right, you know. Let we do as much as you can today, and then we probably schedule next seminar. What, Dima, you think about?
I agree absolutely. The next seminar in 2 weeks is the next slot in 2 weeks is free, so it would be very very good to continue in this rhythm, this exposition.
Okay.
Okay, so
for me,
let's do that. Yeah.
If the audience needs, for me it's okay. I would like to go slowly and to explain all what is necessary to explain.
Yeah, that's great. That's great. Thank you.
Okay, and now
then a small comment. So if you just you see that at the end of this line, you see almost upper triangular matrices, but not with respect to main diagonal, but with respect to other diagonal. And for such matrices, there is also factorization from the roots. So if you consider just usual matrix, so for root alpha I, you just put 1, 1, 1. So you take the alpha I of t, it is just 1, 1, 1, and on the ith row, you have 1 and t. And so therefore, in this case, you have also factorization, and then this is property which you have. It would be exactly for such a factorization from just from algebra. And this is called Dusik parameterization of upper triangular matrices. It's just side comment.
Yeah,
because we're slow.
Okay, this upper triangularity from the opposite diagonality is important here. Okay, just also for making calculations. And now I would like to go to the geometric part of the four-dimensional consistency. So if you would like to understand this consistency for the Zark maps, where you have some lines, some collinearities, then in the heart of the multidimensional consistency is the so-called Zark theorem. And because of that, I coined the name the Zark map. Yes. And what is the Zark theorem? So suppose you have two triangles in perspective from a point, which means that the lines intersecting the corresponding vertices of the triangles intersect in one point. Then, if you consider lines of intersection of the corresponding sides of the triangles, yes, so you have three such lines that then if the triangles are in perspective from a point, then these 3 points, intersection points of the corresponding sides, are collinear. And this is a condition if and only if. So perspectivity from the point, if and only if, perspectivity from a line. Yes. And it turns out that the Zark theorem is a theorem in projective geometries of dimension 3 and more. For projective planes, we should consider it as an axiom to have projective geometries over division rings. Yes. But I wouldn't like to go deeper into this part of axiomatization of projective geometry. the important part from the point of view of integrable systems is first this the Desargues map, but also its symmetry. The formulation of the Desargues map, as you have on this figure, somehow distinguishes one point, the center of projectivity, and it distinguishes one line, the line of the axis of projectivity. But it turns out that in the Desargues map, in the Desargues configuration, through each point there go 3 lines, and each line contains 3 points of the configuration. Moreover, any point of the configuration can serve as projectivity center of 2 triangles. And any line of this configuration can serve as axis of the projectivity. So you should just play with figures starting from a point, trying to write to see the corresponding triangles. Yes. So the symmetry group of the Desargues configuration is S5, in the sense that you can label the lines using 2 letters, you can label the points using 3 letters, and point belongs to a line if the letters of the point contain letters, the set of letters of the point contains the set of letters of the corresponding line. And by the standard point line duality, you also have even bigger symmetry, but we will not need it. But just as a remark, the corresponding symmetric description of the Hirota equation, which initially I formulated on Zn integer lattice. So to have its very beautiful and symmetric description, you should consider root lattice of type A, and then the symmetry group of the Hirota equation turns out to be the corresponding affine Weyl symmetry group of the root lattice. Yes. And because we work with geometry, one can have another gauge. Yes, we can have the same geometric situation, but consider different variables, different gauge. So now collinearity of points represented by phi, phi I, and phi j. So in this case by phi, phi 1, and phi 2. If you consider just standard vector description of points of the affine plane, of the affine space, yes, just collinearity of points, it is just proportionality of the corresponding vectors, yes. Then you can formulate the same geometric situation in terms of another field. Now let us call it field X. Yes. And we can formulate the same geometric transformation using another field, field X. Yes. And here, if you calculate just from this lax representation the corresponding equation, the corresponding relation, it looks as follows. Yes, a bit more complicated, but also it has the local Yang-Baxter description in terms of another matrix. Yes, I didn't put it in the slides, but it is contained in my paper with Rinat Kashaev. Okay. And somehow the next slide involves the decomposition of the map using the symmetry of the Desargues configuration. Okay. So what implies the S5 symmetry of the Desargues configuration on the level of the map? Yes. And so how much time do I have?
Adam, as you like. So 20 minutes.
Okay. Okay. Because I would need this pentagon representation for discussion of the quantum ultra-local reduction. But I will provide this quantum reduction maybe in 2 weeks. Okay, so it turns out that if we have this map for x in x variables, yes, one can decompose this map into 3 parts. First map N, yes, which involves 2 variables. So such a simpler map, yes, which satisfies the following condition, which looks like a degenerated version of the Yang-Baxter equation. Yes. And you can check, you can verify this map, that this map satisfies this condition. Then the next part of the decomposition is another map.
Oh, excuse me, and in this map, so it's there is no any misprint because x1 prime on x2 prime is equal x1.
X1
prime equal multiple x2 prime is equal x1. So is it correct, or it has to be x1 x2?
X1 prime multiplied by x2 prime is equal x1.
Is it correct?
It's just a moment. I should check in the original version, but it should be. One moment. X1. Yes, yes, it is. I think it is correct.
Okay, thank you.
Okay, because you can see that these maps, if you have the normalization map, indeed, x1 prime, so x2 prime multiplied by x1 prime is equal x1, yes? And here is something similar, but a kind of indices are reversed. So a kind of inverse and indices are reversed. Yes. So if you calculate the inverse of the normalization map, you obtain the Veblen map, but up to some change of index 1 into 2. So this is another map which satisfied the similar pentagonal condition, but in reversed order. Yes. And the P is just the transposition, permutation of two variables. Yes. And I would like to somehow to comment for those who are interested in quantum groups, or in general in the Hopf algebras. Then if you have a Hopf algebra, then naturally you have a kind of map which satisfies the quantum pentagonal condition. So from general theory of Hopf algebras and quantum groups, the pentagonal condition is even more important.
So just excuse me, but I want to say that for Weyl map, we have the following formula: 1 minus x1 bar multiple on x2 equal 1 minus x1 multiple on x2. So there is some preservation law. And
yes.
For the first map, so I
Yes.
don't see any preservation laws. So in some sense, yeah. So. Okay.
But I think these maps are very much related. In my paper, I discuss these relations.
Yeah, but for Weyl map, we have some formula. This is like 1 minus x1 bar multiple on x2 bar is equal 1 minus x1 multiple on x2. And so therefore, I guess that for the first map, it has to be some ELSA kind of preservation relation.
Yes, so there is, certainly there is. I can now I trying to see in the paper, but as you can check that the inverse of the normalization map satisfies the reversed pentagonal condition. Okay, and now I would like to explain the geometric meaning of these two maps. So what is the normalization map? You have this collinearity of 4 points on the line. Yes, and you can arrange triples for which you can have two linear equations. So for A, B, C, you have one equation of this form. For A, C, D, another equation. Yes, but it fixes the configuration of the 4 points. Yes, and you have another equation for A, B, D, and for B, C, D points. Yes, and these relations are somehow not independent, of course, because they just deal with the same 4 points on the line, and this is the mutual relation of this x1 and x2 and x1 prime and x2 prime. So it was for 4 points on the line, and now Veblen map. Why Veblen? Because this configuration of points, so we have 4 points, so 4 lines and 6 points. This configuration is in the in projective geometry called the Veblen configuration. So basically, if you have this 5 black points, you can calculate the 6th point, BD, like here. So this is the equation for 2 lines. And this is equation for the same configuration, which involves 2 opposite lines. And this is just the transition between these 2 description of the same configuration. And now I will go back to show you the definition of the Desargues map. Yes, you can see we have here initial 4 points on the line. Yes, and then we have the Veblen configuration. So this splitting of the map of the Hirota map in the affine gauge follows just from the same picture, but is decomposed into 4 points on the line and on the Veblen configuration. Okay. And in the paper by Sergeev and Kashaev, they studied maps of this form. So we have map decomposed into maps N and V, which satisfy the pentagonal and reversed pentagonal condition. And they asked a question, under which condition such pentagonal maps give you a solution of the Zamolodchikov equation. Yes. And they found that such a map satisfies the Zamolodchikov condition, provided the following matching condition between maps is satisfied. Yes, so this is a kind of compatibility for 2 pentagonal maps. And in the geometric interpretation, this condition can be understood as follows, that you start from these black points, which are arranged on, so 4 points are on the initial line, and other points are on these 2 lines. And now, using the normalization map and the Veblen map, you try to construct the other remaining points of the star configuration. And you can go from the right side or from the left. Yes. And in our geometric description, you can see that this is the condition that the result is the same, independently what you start from. So this is the first part of my talk, and I think it is the good time to break it. if you
Yes,
agree.
it's okay.
And just to recapitulate, I presented you the construction of the map which satisfies the Zamolodchikov condition, starting from the Hirota, from the geometric interpretation of the Hirota equation, and from geometric interpretation of its multidimensional consistency. And as geometry naturally somehow suggests, the maps can be defined for non-commuting variables. And somehow this is the most, I think, generic picture we have for interpretation of the non-commutative Hirota equation. And we considered two simple different gauges, the Hirota gauge and the affine gauge. And they both give the corresponding solution to the Zamolodchikov equation. And so I also presented you the geometric meaning of the decomposition of the Hirota map into the Veblen and normalization map. And what is somehow important, that sometimes we should not fix the gauge on the very beginning. Here, to somehow to define a map, I had to fix a gauge. If we do not fix a gauge, then we will have more free parameters within the map, but we can try to play now with other conditions. So an example what gives you, if you start with some freedom for the maps. So I will present in the second part of my talk, hopefully in 2 weeks. Okay. Okay, so I think I will stop here.
Perfect. Adam, but do you think that this decomposition of the solution of the tetrahedron equation is in a sense generic? So,
so generic is in the sense that more generic will be if we consider the generic gauge. Yes, but you mean, but probably you would like to have something more. Would like to have a kind of theorem that if you have a solution of the tetrahedron equation, then you can decompose it into this two pentagonal maps and a permutation. Yes, I think it is not true, because there are known more complicated Zamolodchikov maps, which I think geometrically can be also decomposed into several Veblen and normalization maps, but not only two. I mean, if you consider the so-called discrete the non-commutative discrete Darboux equations, somehow sometimes called the discrete two-wave equation, then the corresponding companion map also satisfies the Zamolodchikov condition. But I think at least I cannot geometrically see a way how this more complicated map related to discrete Darboux equations could be decomposed into two pentagonal maps. Probably it can be decomposed into pentagonal maps, but you need more maps. I mean,
you see, we have discussed with Gleb Kashaev some years ago very simple combinatorial picture. So the tetrahedron equation comes from the combinatorics of the 4-cube, and if you consider its sections just by hyperplanes, you obtain something like the Pachner moves in these sections. And the 3-2 Pachner move is related to the pentagon equation.
yes.
So is it known, is it related to your construction?
You see, probably, so my construction for the discrete Darboux equation, or for the, in fact, for discrete Darboux equation, the combinatorics is more or less the same like geometry, yes? Because the discrete Darboux equation geometrically just deals directly with 4-dimensional, with 3- and 4-dimensional cubes. It is known that 3-dimensional discrete Darboux equation can be obtained from 5-dimensional Hirota equation, in the sense that if you start from the discrete KP equation from the Hirota equation using 5 discrete variables, there is a way how to, after some change of variables, there is a way how to obtain the discrete Darboux or discrete two-wave equation. So this means that there is a way how to decompose this Zamolodchikov equation related to 4-dimensional cube into a sequence of Veblen and normalization maps. But the decomposition wouldn't be so simple like here. So
okay, but what I said, it doesn't depend on the specific solution of the tetrahedron equation. So it's just the definition of it. So in hyperplanes, it resembles the pentagon equation. Just by definition, it's not related with the geometry, the projective.
Yes, understand that combinatorially it also, I mean, it resembles this configuration. But the point is how many sections somehow you need to build the map.
Okay.
Yes.
Dima, I saw in this participant list that there were questions by George Papamikos and Ed Corrigan. Maybe.
I have not read. Could you read it?
They raised their hand.
So there is.
Yeah. Okay. Sorry.
So there is a question, or.
Yeah. So yeah, someone raises their hand. So it's.
Okay.
I didn't want to ask, just clap my hands.
Sorry.
Okay.
Can I ask a question then? This simple matrix refactorization problem is a generator of Yang-Baxter maps, and the local Yang-Baxter equation is a generator of tetrahedron maps. So is there any relation with, you probably said something I missed, between the pentagon maps and the matrix refactorization problem?
Pentagon and refactorization. I should check. Maybe we wrote something with Sergey Sergeev about that, but I think I do not remember.
Yeah,
I do not.
Thank you.
If you know something, I would like to know.
I will check in your work with Sergey. I don't know anything.
So I do not remember any kind of refactorization for the pentagon map.
Okay.
Yes.
Thank you very much. We continue in 2 weeks. Adam, could you provide us your slides for better preparation?
Of course. So what I can do it? Just I can send it to you.
Yes, yes.
If it's okay.
It's
okay.
Thank you, everybody, and we will meet in 2 weeks.
Okay. Thank you
Thank
very
you,
much.
Thank you, Adam.
For listening.
Thank you.
Thank you, and for the question and some partial comments. Thank you very much.
Thank you. Bye.